Today we're going to talk about section 2, which is on units, and then we'll focus on the second part of this with accuracy and precision and the difference between the two. We will also finish off at the very end with the equation for density, which we're going to use throughout this year. I didn't get to talk about this at the end of the last class, but I wanted to briefly mention where we come up with the base units for the SI system and how we define them. So if you recall, in 1960, scientists got together and wanted to define specifically what these units were. It's not that they didn't exist before then, it's just that we didn't have a very clearly defined what this unit is for all time. And so the first one here is time. How do you define time, right? The unit here was a second, okay? I wouldn't really worry too much about the technical lingo of what's going on here because it's a lot of stuff that's probably a little bit over your understanding right now, but essentially here's what they did. So they knew what a second was time-wise, but to make sure that it was always the same, okay, going forward, they picked an atom. The element was cesium. Its atomic mass was 133. And they counted how many times this thing gave off radiation in 1 second. So atoms, even at very cold temperatures, okay, they will have very small movements, almost like vibrations. And when they do, they'll give off radiation, okay? And they counted in 1 second, this particular atom gave off 9,192,631,770, okay, amounts of vibrations or radiation. And then they said that's what 1 second is. This guy up here in the picture, he's wearing an atomic clock. It's running on a cesium, is actually what it's using, right, to figure out exactly how long 1 second is. That's what that is up there. So don't worry about writing down this definition word for word because it's kind of a lot of technical stuff, but try to use your own words to describe that, right? This thing is kind of more or less vibrating back and forth, and they counted this many times and said that is 1 second. Okay, the second one here is length. How does it define? It used to be actually sort of a fraction of how far it was from the equator, I believe, to the North Pole, but then we later found out that the Earth isn't obviously a perfect sphere, so that distance changed depending on where you were on the equator as to how far it was going to take you to get to the North Pole. So then we went off of this sort of marking on the side of a building here. I don't know if you can read it, it says meter, and there's a line here and a line here, and this was what the official definition for a meter was for a long time. But that's not super helpful because, well, this thing can deteriorate, right? Okay, it's outside, it's exposed to the elements, okay, it can erode, and that would change the definition of what a meter is. So instead, scientists pick something that's very consistent and shouldn't change, and they said that, okay, well, instead of this, let's say that we'll use light as our way to define a meter. It says that the distance light travels in a vacuum in 792,458th of a second. So about 1/300 millionth of a second. That's how long it takes light to go that distance. Okay, it's about, roughly in American units, or in America units, it's about 39 inches or so. Okay, it's a little over 3 feet. But that means in 1 second, light travels about 300 million meters, right? If you do the opposite of that, right? If you let it go for 1 second, it goes about 300 million meters, okay? All right, the SI unit for mass is kilogram. So how did we come up with a standard kilogram? Right, mass was the measure of the amount of matter an object contains. It's based on these cylinders, platinum and iridium cylinders, over in, I believe it's kept in France. They're kept in sterile conditions. So you can see here, here's our cylinder made out of platinum or iridium. It's kept inside of a glass container, which is kept inside of another glass container. Inside of here is a vacuum, meaning there's no gas, and inside of here is a vacuum, meaning that there's no gas. So this thing is prevented from any sort of air out here, right, getting into the glass, right? Okay, can't get to it. Additionally, platinum and iridium, okay, they're part of the noble metals. They do not oxidize. They don't rust, right? So over time, they're not going to add oxygen to the mass of this. So even if somehow we're able to get to it, it shouldn't react with it. So this thing should stay 1 kilogram, presumably forever. Okay. All right, the next one here, temperature. We'll say some more on it on the next slide as well, but temperature is the measurement of average kinetic energy of the particles that make up an object. This is super important. Kinetic energy is the energy of motion. Okay, temperature is really a measure of how fast or slow something is going. That's what it means. Okay, so as it says underneath there, things that are moving faster, right? Okay. This is hotter, right? Assuming it's the same substance, okay? This is slower, right? This is colder. Okay, things that are faster move hotter. Temperature is just a numeric representation of that, okay, movement. All right, it's movement, average of the kinetic energy. If you take physics, you'll talk about kinetic energy a lot. So as I said just a second ago, as motion increases, temperature increases. We have three scales: Fahrenheit, Celsius, and Kelvin. We're not going to really use Fahrenheit in class other than to maybe just give you a point of reference. Celsius, we might record some temperatures in Celsius. Later on when we start doing stuff with calculations towards the end of the year, we're going to want stuff in Kelvin. We'll talk about why here in just a moment. Okay, our three scales. The first one, Fahrenheit, it came about in 1724. Basically, guy has his thermometer, puts his own tick marks on it, right? And then finds the point at which water freezes. Let's just say it's right here. Okay, and then finds the point at which water boils. It's up here. And says this one's 32 degrees, this one's 212 degrees. And that was just based off of his markings. This gave us a first thermometer, first scale to use. The problem was that this was relative, right? It was all just based on whatever random numbers he put over here. Now we got a relative scale, okay, compared to one another, but we did not get an absolute scale. Okay, so the scale isn't really based on anything other than what this guy just randomly put right on your thermometer. The second one, Celsius. Okay, another scientist, he comes along and says, okay, great, let's change this instead. Let's make this 0 degrees, and let's make this 100 degrees. So now it's at least based off of the point at which water freezes and boils, water freezing at 0 degrees and boiling at 100 degrees. Okay, so that's a little bit better. It's at least got some sort of standard that we are basing it off of, but it is still a relative scale. Okay, down beneath here, that's the equation to go from to get to Fahrenheit. If given Celsius, you can rearrange it to solve for C if you need to solve for Celsius, right? You guys should know enough algebra to do that. Well, this is all good and all. Celsius improved the scale. The problem was that we can still have negative temperatures. Okay, and that may not seem like a huge thing, but the problem is temperature is measuring motion, right? And if you're saying you have negative temperature, we're not talking about negative motion, right? So how does that make sense? And plus, if we're putting stuff into an equation later on this year, when one of the variables becomes negative, that really complicates things. Okay, so we needed a scale that actually had a no movement point, right? Okay, a point where 0 meant no motion at all, because in both of these scales, things are still moving at 0, right? Okay, at 0 Celsius, okay, those particles are still moving. At 0 Fahrenheit, even though it would be beneath the scale here, right? 0 Fahrenheit, things are still moving. We're talking about absolute 0 with no motion. That was found out by a guy named Lord Kelvin. Later on this year, we might talk about how he did this. But for right now, it's enough to know that he's going to determine that point. He finds the absolute 0 point and calls that 0 Kelvin. And the equation to convert between Celsius and Kelvin is Kelvin equals degrees Celsius plus 273. Notice when I am saying this, I don't say not, right? It's not degrees Kelvin, okay? I just say Kelvin, right? Okay, you just go 0 Kelvin. Because it's not a degree of something. It's not part of a relative scale. It's an absolute scale. So we just say whatever number Kelvin when we're talking about it. But later on this year when we're putting stuff into equations, we have to have things in Kelvin because it needs that no negative temperatures. That's what this means, right? We can't go below 0. All right, and then lastly here, so we talked about some of the base units. There are some more. We're going to talk about moles a lot later this year, but kind of going past base units, the other units are called derived units, and that's some sort of combination of your base units, okay? So for instance here, the most common one that we're going to use this year is volume. Volume is really distance in 3 dimensions, right? If you take a regular prism up here, rectangular prism, right? Width is really a measurement of distance, right? Length is a measurement of distance. Height is a measurement of distance. And when you're multiplying all those together to find the volume, okay, you're really taking distance times distance times distance, which gives you distance in 3 dimensions, right? Which is what this is, okay? Volume is space occupied by an object. So you can do it by measuring the dimensions of the object and then plugging it into an equation, right? If you're talking about a rectangular prism, there's other shapes as well, okay? The official SI unit is a cubic meter, okay? But if we stop and kind of think about what that means, that is a really big unit, right? That's like, a little over 3 feet on each side. And so that's kind of a large, clunky unit. We're not going to use that often in chemistry. You might in physics if you're talking about the volumes of large things. Usually we're going to use smaller things. We're going to use liters. And 1 liter is 1 cubic decimeter. You might have seen that on your previous homework. I'm probably not going to count you wrong on that if you missed it, but that's what that means. A liter is a cubic decimeter. So instead of 1 meter on each side, it's a tenth of a meter. Okay, so 3.9 inches or so on each side. Okay, and that would be what 1 liter is. And then another one that we're going to commonly use here is just milliliters. Whoops, let me undo that. This guy right here, 1 milliliter is equal to 1 cubic centimeter. We're going to see that quite frequently. Another way to find the volume of something that's not a regular shape, right, that we can't just plug things into an equation, is by using water displacement. And we're going to talk about that here in just a few minutes. We're talking about calculating density and ways to calculate density. Switching gears here, the second part of today, we're going to talk about accuracy and precision and then give you the density equation. So this is shifting away from units for just a moment. When scientists make measurements in lab, they're never certain, okay? So if you think back to that example of that Hope diamond, right, the big blue diamond, we said that there were roughly, 4.6 times 10 to the 23rd atoms in that thing, right? That's not an exact number, right? We have not counted every single thing in that diamond. It would just take way too long. But we have a rough approximation, okay? We know it to a certain amount of certainty. And that's actually going to be super important later on when we're talking about reporting data. But when scientists make measurements, they're never perfectly certain. We can get really good measurements with better equipment, but never perfect. Okay, so when we are looking at data, you need to evaluate the accuracy and precision of that data. And these two things aren't the same thing. I know in kind of everyday English vernacular, you could say something, oh, that was really accurate, or that was really precise. And it kind of means the same thing, when we're just speaking. But when we're talking about analyzing your data, there's a difference between the two. So we'll give you the definition, and if you're not quite sure what the difference is between the two, hopefully the next slide will illustrate that for you. So accuracy is how close a measured value is to what the accepted value actually is. So how close did you get to what you were supposed to get, or what the scientific community agrees upon as being the correct value, at least right now. The term precision refers to how close a series of measurements are to one another. So this is you've done multiple measurements over and over again. How close are they to what you got before? Okay, so those are just what the definitions are. If you're not sure what the difference is, here in just a moment, we'll show you. Okay, so first we're going to look at accuracy and precision in terms of like an archery target. Perhaps, some of you might be bow hunters when the season arises. Let's say you're in the market for, purchasing a new bow, okay? So you go to the store, and you pick up the first bow you find, and they tell you, okay, why don't you take it out back and, try it on the target and see how well you do, right? Okay? So you knock an arrow, you pull it back, right? Aim it, look down the sight, you shoot one arrow, and you hit right in the middle, right? Bullseye, okay? You took one shot, and you hit perfectly. Okay? Your one shot was accurate. You don't know for sure that that's a great bow. It could just be that you got very lucky and you shot perfectly on the one shot that you did shoot. Okay, so you picked up one bow, you took one shot, right? You hit the target. The most we can say is, hey, that one shot was accurate. We can't really say a whole lot about the bow, but we can say your one shot was accurate. Okay? All right, so you put that bow down, you pick up a second bow. All right? And you knock an arrow, right? Aim down the sight, aim right at the middle of the target, goes off to the left. Okay, well, maybe you flinched at the last second, so let's try it again. Okay, so pull back the arrow, right, aim down the sight, and release, and it goes off to the left. Okay, maybe I just did the same mistake twice in a row. Let's try a third time, just to make sure. So same thing, okay, aim down the middle, and it goes off to the left. At this point, you're pretty sure you're not flinching to the same exact spot every single time. You're pretty sure there's something not quite right with the bow. Perhaps the sight needs to get calibrated a little bit better, because it seems to not be going where you think it's going. Okay, In this situation, we would say this bow is precise but not accurate, meaning that, right, we got the same spot every time, we got the same result every time, but it's not the result that we wanted or the result that we should have gotten, right, aiming it here. Okay, so this is a bow that would be precise but not accurate. Right, it's getting the same results but not the results that you necessarily are looking for. Okay, so you put that bow number 2 down, you pick up bow number 3. All right, knock an arrow, aim down the sight, hit right down the middle. Cool, maybe I was just really lucky. Let's try it again. And you get the same results. And you do it a third time just to make sure. Okay, and all 3 hit right there in the middle of the target. You would say that bow is accurate and precise. It's hitting exactly where it's supposed to be, and it's hitting that same spot over and over again. Okay, that's different than over here because this is not hitting where we want it to. Okay, so you put this bow down. You kind of like this one, right? Bow number 3. You put this one down, and you go over and find bow number 4 on the sale rack. Okay, it's the cheapest of the bunch. You pick it up. Like, cool, maybe I can get a bow for cheap. Aim down the sight right at the middle, and it goes up and to the left. Okay, well, all right, maybe it's precise, but we're going to have to take more shots to figure that out. It's at least not accurate. Take a second shot, down to the left. Okay, now I'm not getting the same result, and I'm not hitting where I want to hit. All right, aim down the middle, third shot. Okay, off to the right. So, this last bow, okay, is not precise or accurate. We're not getting in the same spot, okay, and we're not hitting the target that we want to hit, okay? So that's the difference between the two, all right? Now, if you're in the store, picking out bows and you want the best one, you're probably going to want, right, this one, the accurate and precise bow, okay? It's giving you the best results, right? You don't want to miss on your shots if you're out there hunting, so this is the one that you'd want. Now, typically, though, this is also probably the most expensive, right? Okay, you usually pay for good equipment, okay? This one over here is probably the cheapest. There's a reason it's on sale, okay? Nobody wants it because it's not very good. It's at least, allows you to shoot arrows, but you're not really hitting where you are aiming. This one would be cheap. And so why do we mention that? Well, when we are in lab this year, okay, some of our equipment is cheap, right? It doesn't serve a whole lot of purpose. It's not accurate or precise. Its job is just to, I don't know, hold some solids or hold some liquids. It doesn't really matter how much is in there, okay? It's not trying to be accurate or precise. It's just simply doing some simple function. These things are usually pretty cheap. We have some flasks, okay? This is what flasks kind of look like in my quick drawing of it. We have some flasks that cost like, I don't know, 5 cents, okay? We can order a whole bunch of those. Not that you should, aim to break glass in a lab because that's a problem, but, if you break one of those, it's not an issue, okay? We have some other flasks in the lab, okay, that are very, very accurate and precise, all right? And these things run like $75, right? These things over here are like 5 cents. So this one is very accurate and precise. You pay a lot of money for that, right? This one is super cheap. The scales that we use in lab typically go out to the hundredths place when we're measuring mass, okay? These things cost about, I don't know, $80, something like that, okay? We have a scale over in lab that goes out to the 10,000ths place when it comes to measuring things, and this thing costs $5,000, right? So my point being here is that when it comes to equipment, you pay for the good stuff, right? If you want something that's accurate and precise, you're going to have to shell out the cash, okay, to make sure you pick up the good one. So that's what it looks like in terms of archery targets, right? If you're talking about evaluating your equipment here, about evaluating your bows. But what about if we're looking at data? So let's try looking at a table here and see if we can pick out what's accurate and precise. Okay, here we've got 3 students. They're in a lab, and their job is to determine the density of a solid that they are given. Now, they are given sucrose, which is table sugar, okay, which has the actual density of 1.59 grams per cubic centimeter. All right, so 3 students, A, B, and C. If we take a look here, we got 3 trials and then an average. So we got student A's data, student B's data, and student C's data. Of the 3, okay, we would say that the one that is the most precise is student C. Take a look here, right? Student C did 3 trials. They got 1.70, 1.69, and 1.71. Each of those values, right, was within 0.02 of each other, right? Okay, so this data is really precise. However, their average 1.70, okay, is not really accurate, because accurate would have been about 1.59. So it's precise, but we'll say not accurate, right? Okay. And then if we go over to, say, student A and look at student A's data, student A's average comes the closest, okay? So we can say that his data was fairly accurate, okay? But we'd say it's not as precise if we look at the trials as student C, not as precise as student C. And then if we look at student B is all over the place. This is not accurate, right? It's at 1.51, not accurate, and it's not precise. The trials are all over the place. Student B either has really bad equipment, okay, so that's what this is telling you here, right? These three trials, okay? This is either bad equipment or bad lab technique, meaning that they're not doing the same thing every time. They keep changing up ever so slightly what they're doing. Okay, so that's how we look at this in terms of data, right? It's not with the archery targets, but this is how you evaluate your data to figure out what's good and what's not so good. Okay, so in addition to the kind of visual inspection of whether something is accurate or precise, there are some mathematical tools that we can apply to data to figure out how good it really is. Okay, and the first here is error. And that's how far from an expected value the experimental value is. Okay, the experimental value is what you get in lab. You can have an expected value. Sometimes this is called the accepted value. Okay, this is just what the scientific community agrees upon. Right, we say that this is what we think it is. Okay, so there's two equations on this page, and here's the first one that you'll want. Error is experimental value minus accepted value. This is your lab value, right, minus what the scientific community agrees on. Okay? That's how you calculate error. Error by itself isn't really super helpful. Really a better way of expressing this is, undo that. A better way of expressing it is this equation here, percent error, okay? And so if you don't have this in your notes yet, put it in your notes. And also, I would highlight it or star it or do something so that you can come back and find this easily, because this is oftentimes if we're doing a lab and the lab asks you to calculate something, one of the last things I'll ask you to do when you're evaluating is to calculate the percent error. Okay, and that equation is percent error equal to the absolute value of error, so whatever this is here, right? Okay, just taking this, right, and plugging it in here, okay? It's the absolute value of that divided by the accepted value times 100. And so because of these absolute value bars, we shouldn't have any negative percent errors. Okay, it should all be positive values. This is really a better way of telling you how good your data really is. You know, we are in a high school science situation. If you have a percent error of 10% or less, you did really well for that lab. Really, even anything under 50% error, you did pretty good. Anything over 100, now you probably made some major mistakes somewhere. But just don't expect to be perfect every lab. Okay, we're limited by our equipment, right? Okay, the more expensive the equipment, the better it is. We're limited as high school students, right? We're not going to be able to just go out and buy the most expensive stuff all the time. But our equipment should be good enough to get close to what we should be getting most of the time. Okay, let's try a problem where we calculate the percent error of something. Okay, we've talked about pennies before. We did them on day 1 of class. This here says, by U.S. Mint regulations, pennies minted after the year 1982 should weigh 2.5 grams. Pennies minted before the year 1982 should weigh 3.11 grams. Now, if we were in class doing this, I'd weigh it out on a scale, and we'd try to do this right in person. I'm just going to tell you what the one was that we did in class last, and then we'll use that data to calculate percent error. And if you recall, in 1982, the U.S. Mint realized that if we keep printing or producing pennies, or we keep minting pennies out of solid copper, we're going to lose a lot of money. So they switched it to being a zinc center with a copper shell around the outside of it. They basically just coated in copper. So the old pennies weigh more, right? They weigh 3.11 grams. The new ones weigh 2.5 grams. If you pick them up, and pick up two different ones, you can actually tell the difference. The one I used in class was from 1959, so it was pretty old. It had a mass of 3.13 grams. Now, I weighed that out on a scale. We would say this is the lab, right? That's the experimental value, okay? The lab or experimental value, okay? Because that's what we measured. It should weigh, according to this data, right? Should weigh 3.11 grams, right? This is the accepted value. That's how much it should weigh. So let's calculate a percent error, right? This thing is a pretty old penny, right? Things happen to pennies over the time, right? They can rust a little bit, right? They kind of turn that almost a little bit of a green color. They can get gunk on them. People can drop them on concrete and they can get scratched up, so they might lose a little bit of mass. There's all kinds of stuff that can happen. This penny is 62 years old or something like that. So, it's 3.13 grams, so it's gained a little bit of mass over the years. All right, so on the top is the absolute value of error, right? We're going to write this out and actually put in all of our numbers. Divided by the accepted value rate times 100. Well, let's go ahead and plug in what error is, right? That is our experimental value minus the accepted value divided by the accepted value times 100. Okay. And for this situation, my experimental value is what I measured, okay, in lab, which was 3.13 grams, minus the accepted value of 3.11 grams, absolute value bar, divided by the accepted value, 3.11 grams, okay, times 100, right? And I'll tell you usually when to round stuff off or give you a list of rules. I think this was 0.64%. Hopefully I'm correct in remembering that number. 0.64%. So the percent error, right, it's about 0.5% off what it should be. Okay, but that's how you calculate it. So there's oftentimes in lab this year, the last thing I'm going to ask you to do when you're evaluating your data is to calculate the percent error. So make sure you've highlighted or starred that equation or put it like a note on the top of the page of your notebook so you can go back and find it when you need it. Okay, last thing we're going to talk about here is the equation for density. This is really the first true science equation you're going to get from us this year. Density is the amount of mass per unit volume, how much stuff you got packed into certain amounts of space, right? Okay. The equation looks like this, right? Density equals mass over volume. You will oftentimes see me write this like this. Okay? This guy here, this is another Greek letter. You're learning a lot of Greek letters. This is the Greek letter rho. Makes an R sound in the Greek alphabet. And it also means density in equations. Okay? Basically, there's so many other letter D's used in equations in science that we decided to just make this one another Greek letter. So it's a Greek letter rho. It's kind of a combination of a J and a P put together. Right? And M over V is just mass over volume. The common units here, grams per cubic centimeter, grams per milliliter. That's typically what we are going to see in chemistry. Right? This is mass over volume, mass over volume. The cool part about this is, and we'll have a lab doing this, is that when you calculate the density of something, it is specific to the element, it is specific to the compound or whatever it is that you're looking at. So if you have a table with, you can look at all the densities in the table and compare it to what you calculated, you can figure out what's in front of you. All right. So again, density is amount of stuff packed into a certain amount of space, right? This picture here on the right, this is more dense, right? On the left is less dense. There's less mass in the same amount of space. This has got more mass in the same amount of space. And we're going to show you an equation here in just a moment, or a way of solving density that is very important and one that you need to know how to do. Okay. This is the last slide, last example problem. This example problem is a water displacement problem, and I'm going to box this and make a really big deal about it because I'm going to tell you right now, this is going to be on your first unit test. It'll be one of the problems where you have to show your work. It is also going to be on the final. Okay, I'm telling you right now, right? Already, week 2, and you got a question that's going to be on the final. So, the good news is this isn't that hard. You just have to remember what's going on. All right. So this is called water displacement. It means water movement. And we're going to determine the density of something using water. Okay. So here's what the problem says. When a piece of aluminum is placed in a 25 milliliter graduated cylinder that contains 10.5 milliliters of water, the level rises to 13.5 milliliters. Given that the density of the aluminum is 2.7 grams per milliliter, okay, what is the mass of the aluminum? All right, so there's some stuff we got to figure out here, right? We've got our equation for density. Density is mass over volume. We are trying to solve for mass, right? What is the mass of aluminum? So I want M. I am given density, right? Density is 2.7 grams per milliliter. And I'm given several things of volume, right? My initial volume was 10.5 milliliters, and the final volume, right, is 13.5. Okay, so what's going on here? This is called a graduated cylinder. This graduations are these lines here on the side. That's what they're called. If you see things with a bunch of lines on them in a measurement tool, those are called graduations. It's a cylinder. It's made out of glass. You guys will see this when we go over it and do this in lab. What you do is you put water in the bottom of it, and then you place your object in the water, and the water level rises. Right, here's my object. Water level went up. Okay. And then you can find the volume of the object by finding the difference in the volumes here. So my final volume, right, was 13.5 milliliters. VF is what that is. VI is my initial volume. That was 10.5 milliliters. Okay. How you will see this on your homework, right? What's the object, or what's the volume of the object here? How you will see this on your homework, it's the difference between the two, but what you're going to see is looks like a triangle and a V, okay? And that's another Greek letter. That is the Greek letter delta, okay? Just like the, if we're dealing with COVID, the delta variant. All those variants are named after Greek letters of the alphabet. That one's named after delta. It looks like a triangle. In the Greek alphabet, it makes a D sound, okay? So that's what that is. You guys are learning a lot of Greek letters. But the change in volume, what delta means is change in, and you're going to see it. It's not just for V, change in. You'll see it all over the place. It'll be delta M, delta V. If you're taking physics, you'll see delta all the time. It means the change in something. Okay, so if you see delta V, that means the change in volume. Well, here that's calculated by VF minus VI. So my delta V here is 13.5 minus 10.5. The change in volume was 3.0 milliliters. Okay. Great. So if I go back to my original equation here, I need to solve that for mass. So I'm going to rearrange this. Put this down here, right? Okay, I have density as mass over volume. To get M by itself, I'm going to bring V up to the other side, right? Just using algebra 1. So I have mass times density equals volume, okay? And, whoops, sorry. Scratch that. We're going to have volume times density equals mass. There we go, okay? Volume times density equals mass. My volume, okay, is 3.0 milliliters. My density is 2.7 grams per milliliter. Okay, and then simply all I have to do to figure that out, right, is to multiply the two together. I got 3 times 2.7. That object, that piece of aluminum weighs 8.1 grams. Okay, so it's not always just solving for density. Sometimes you can, be asked to solve for the parts of the equation here. And if it's an irregular shaped solid like this piece of aluminum was, we use what's called water displacement. It's still using, the same density equation. It's still using this, okay, but there's a couple other pieces to it because we have to figure out the volume of the object, right? And neither of these directly are the volume of the object. The difference between the two, okay, delta V, is the volume of the object. All right, so part of your homework is going to ask you to calculate the volumes. All right. I'll be back later on, but if you have questions, feel free to reach out and email me. You can also find Mr. Nendick or Coach Soley around school. They'll be glad to help you as well. Coach Soley is usually in room 307 before and after school. and Mr. Nindick's usually in room 302 or the chemistry labs before and after school. So you can ask them for help as well.